In the depths of space, more than 4 billion kilometers from Earth, an ancient wanderer drifts through our solar system, carrying a secret that challenges everything astronomers thought they understood about cosmic mechanics. This visitor from interstellar space appears ordinary at first glance, a dirty snowball of ice and rock trailing a delicate coma of sublimating gases. Yet beneath this familiar appearance lies a puzzle so profound that it threatens to rewrite fundamental physics itself. The object bears the clinical designation 3I/Atlas, marking it as the third confirmed interstellar visitor to cross our solar system's threshold. Unlike its predecessors, however, this cosmic traveler exhibits behavior that defies the most basic laws of motion governing objects in space. Hello, dear listeners, and welcome to our journey through the mysterious physics of 3I/ATLs. Today we explore the perplexing anomaly of an object that appears to weigh far more than nature should allow. Before we continue deeper into this gravitational mystery, take a moment to settle in wherever you are listening, perhaps in bed, on a quiet evening walk, or during a peaceful moment of your day. If stories like this help you relax and discover new wonders, consider subscribing or liking this program. It helps more curious minds connect with these calming explorations. Now let your thoughts drift as we venture into the realm where cosmic giants hide their true nature behind veils of sublimating ice. Every second of every day, as 3I/ATLAS journeys through our solar system, it loses approximately 150 kilograms of material through outgassing. This process occurs as solar radiation heats the comet's surface, transforming solid ice directly into vapor that streams away into space. Such mass loss should act like a natural rocket engine, gradually but measurably altering the object's trajectory according to Newton's fundamental laws of motion. The physics behind this phenomenon are elegantly simple. When material escapes from a comet's surface, conservation of momentum demands that the comet itself must recoil in the opposite direction. This principle governs everything from the thrust of spacecraft engines to the recoil of firearms. The effect, known as non-gravitational acceleration, has been observed and measured in countless comets throughout our solar system's history. For 3I/Atlas, scientists at Harvard University and other prestigious institutions have carefully tracked the comet's position using data from over 200 observatories worldwide. These measurements, precise to fractions of arc-seconds across billions of kilometers, should reveal the subtle deviations from a purely gravitational trajectory that outgassing inevitably produces. Yet the results confound expectations. Despite losing the equivalent of a small automobile's worth of mass every few minutes, 3I/ATLAS continues along its path, with barely perceptible deviation from pure gravitational motion. The object behaves as though it possesses such enormous mass that the rocket-like thrust of outgassing cannot meaningfully alter its trajectory. This observation leads to an extraordinary conclusion. Using established principles of momentum conservation, researchers calculate that 3I/ATLs must possess a mass exceeding 33 billion tons. To appreciate this figure's magnitude, consider that it represents approximately 6 million times the mass of the Great Pyramid of Giza, all contained within what appears to be a relatively modest comet nucleus. The implications extend far beyond simple curiosity about a single object's properties. Comets of such enormous mass should be extraordinarily rare in the galaxy's population of wandering objects. Statistical models suggest that discovering one such massive interstellar visitor should occur only after observing approximately 100,000 smaller ones. Yet 3I/ATAs arrived as merely the third confirmed interstellar object ever detected. This statistical anomaly creates what scientists term a population crisis. Either our understanding of interstellar object formation and ejection mechanisms is fundamentally flawed, or 3I/Atlas represents something unprecedented in astronomical observation. The object appears to violate the expected size distribution that governs populations of cosmic debris throughout the galaxy. Furthermore, the mystery deepens when considering the observational techniques used to estimate the comet's size. Traditional methods rely on measuring reflected sunlight to determine an object's cross-sectional area, from which diameter estimates follow. For 3I/Atlas, these optical measurements suggest a nucleus diameter of perhaps a few kilometers at most, hardly extraordinary by cometary standards. The disconnect between apparent size and calculated mass presents a density paradox that challenges conventional understanding of cometary composition. If the mass calculations prove correct, 3I/AT must possess a bulk density far exceeding that of typical comets, which consist primarily of loose aggregations of ice and dust with significant porosity. Normal comets exhibit densities ranging from 300 to 800 kilograms per cubic meter, roughly comparable to freshly fallen snow or pumice stone. Such low densities result from the porous rubble pile structure that characterizes most small bodies in space. For 3I/AT to achieve its calculated mass within its apparent volume would require densities approaching those of solid rock or even metallic materials. This possibility raises fundamental questions about the object's formation history and composition. Could 3I/AT contain a core of unusually dense material surrounded by a more typical cometary mantle? Might it incorporate exotic forms of ice compressed under extreme conditions, or does its structure represent something entirely outside current theoretical frameworks for understanding interstellar objects? The puzzle extends to the mechanism by which such dense material could form in the first place. Comets typically originate in the cold, low-pressure environments of planetary system peripheries, where gravitational compression cannot generate the extreme densities implied by 3I/AT's behavior. Creating such compact material would require processes more characteristic of planetary interiors or stellar remnants than cometary nurseries. Alternative explanations focus on observational uncertainties and measurement limitations. Perhaps the outgassing rate measurements underestimate the true mass loss, or systematic errors in trajectory determination mask subtle non-gravitational accelerations. However, multiple independent observational campaigns using different techniques and instruments converge on similar results, lending credibility to the basic measurements. The mystery of 3I/AT's excessive mass represents more than academic curiosity. It challenges fundamental assumptions about the nature of interstellar space and the objects that traverse it. Understanding this anomaly may require developing new theoretical frameworks that bridge planetary science, stellar dynamics, and galactic evolution. As this ancient traveler continues its journey through our solar system, each observation adds new pieces to a cosmic puzzle that refuses easy solution. The silent giant maintains its secrets behind a facade of ordinary cometary activity, reminding us that the universe often conceals its most profound mysteries within seemingly familiar phenomena. In the darkness between stars, forces, and processes beyond current understanding may forge objects that defy conventional categorization. 3I/AT serves as a messenger from these distant realms, carrying within its enigmatic bulk the potential to revolutionize our comprehension of cosmic mechanics and the fundamental nature of matter in interstellar space. The comet's passage through our solar system offers a unique opportunity to study this anomaly in detail, potentially unlocking secrets that have remained hidden throughout billions of years of galactic wandering. Each spectrum, each trajectory measurement, each careful observation brings scientists closer to unraveling the mystery of why this cosmic visitor weighs so much more than it should, according to everything we thought we knew about the physics of space. Newton's laws of motion govern every interaction in the universe, from falling apples to orbiting planets to spacecraft traversing the void between worlds. These fundamental principles, unchanged since their formulation over 3 centuries ago, provide the mathematical foundation for understanding how objects move through space and respond to forces acting upon them. The third law stands as perhaps the most elegant and universal. For every action, there exists an equal and opposite reaction. This principle explains the thrust that propels rockets through space, the recoil that pushes a rifle backward when fired, and the subtle acceleration that should affect every outgassing comet in our solar system. Yet 3I/AT challenges these time-tested principles in ways that perplex scientists and demand explanation. The comet appears to violate conservation of momentum itself, one of physics' most sacred and inviolable laws. When a comet approaches the sun, solar radiation heats its surface, causing volatile materials like water ice and frozen carbon dioxide to sublimate directly from solid to gas. This process creates the characteristic coma and tail that make comets visible to Earth-based observers. The escaping gases carry momentum away from the nucleus, and by Newton's third law, the nucleus must recoil in the opposite direction with equal momentum. This rocket-like effect, known as non-gravitational acceleration, has been observed and measured in hundreds of comets throughout astronomical history. The phenomenon provides valuable insights into cometary composition, internal structure, and thermal properties. For most comets, these accelerations are small but readily detectable with modern observational techniques. The mathematics describing this process are straightforward and well established. The thrust generated by outgassing depends on the mass loss rate, the velocity of escaping gases, and the efficiency with which momentum transfers from gas to nucleus. Given knowledge of these parameters, scientists can predict the resulting trajectory changes with remarkable accuracy. For a typical comet losing material at rates comparable to 3I/Atlas, the expected acceleration should produce measurable changes in orbital elements over observational timescales of months to years. These changes manifest as gradual shifts in the comet's position relative to predictions based purely on gravitational dynamics. Sophisticated computer models incorporate these non-gravitational forces alongside gravitational perturbations from planets and other solar system bodies. The resulting calculations can predict comet trajectories with extraordinary precision, often accurate enough to guide spacecraft encounters and predict return periods centuries into the future. 3I/Atlas confounds these established methods through its apparent immunity to momentum conservation. Despite losing approximately 150 kilograms of material per second, the comet shows virtually no deviation from a trajectory determined solely by the Sun's gravitational pull. This behavior suggests either a fundamental misunderstanding of the outgassing process or the presence of enormous hidden mass. The rocket equation, derived from conservation of momentum, provides a quantitative framework for understanding this paradox. This equation relates the velocity change of an object to its mass ratio before and after fuel consumption. For spacecraft, the equation determines how much fuel is required to achieve desired velocity changes. For comets, it reveals the trajectory modifications that outgassing should produce. Applying the rocket equation to 3I/Atlas yields results that strain credibility. To maintain its observed trajectory while losing material at measured rates, the comet would need to possess a mass-to-outgassing ratio far exceeding that of any known cometary object. The calculations suggest a total mass on the order of tens of billions of tons, a figure that places 3I/Atlas in a category entirely its own among interstellar visitors. This mass estimate creates immediate problems for understanding the object's physical properties. Combining the calculated mass with optical size estimates yields bulk densities approaching those of solid rock or metal, materials fundamentally incompatible with active cometary behavior. True rocky or metallic objects lack the volatile components necessary to produce the observed outgassing. The paradox deepens when considering the efficiency of momentum transfer between outgassing materials and the nucleus. This efficiency, characterized by a parameter called the momentum coupling coefficient, determines how effectively escaping gases impart thrust to the parent body. For most comets, this coefficient ranges from about 0.3 to 0.7, meaning that 30 to 70% of the gas momentum transfers to the nucleus. Even if 3I/Atlas exhibited perfect momentum coupling, meaning 100% of the outgassing momentum affected its trajectory, the observed mass loss rates would produce readily detectable accelerations for any reasonably sized object. The absence of such accelerations implies either catastrophically inefficient momentum transfer or extraordinary mass hidden within the nucleus. Laboratory studies of momentum transfer in outgassing systems provide additional perspective on this puzzle. Researchers have investigated how sublimating materials interact with porous substrates, measuring the fraction of escaping momentum that couples to the solid matrix. These experiments consistently show significant momentum transfer occurs whenever volatile materials sublimate from solid surfaces. The fundamental physics underlying momentum conservation admit no exceptions or special cases. The law represents a direct consequence of the universe's translational symmetry, the principle that physical laws remain unchanged when moved from one location to another. Violating momentum conservation would require abandoning our most basic understanding of space and time. Alternative explanations for 3I/Atlas behavior must therefore invoke more subtle physical mechanisms while respecting conservation laws. Perhaps the outgassing occurs in perfectly isotropic patterns that cancel out directional thrust components. However, such symmetrical outgassing would be remarkable given the irregular shapes and compositions typical of cometary nuclei. Another possibility involves the presence of internal structure that redirects momentum transfer in unexpected ways. Complex internal cavities, fracture networks, or compositional heterogeneities might channel escaping gases in directions that minimize net thrust on the nucleus. Yet even highly irregular outgassing patterns typically produce measurable non-gravitational accelerations. The temporal evolution of 3I/ATLAS's outgassing provides additional constraints on possible explanations. Observations reveal relatively steady mass loss rates over periods of months, suggesting stable sublimation processes rather than sporadic or episodic activity. Such consistency argues against exotic mechanisms involving sudden structural changes or unusual thermal behavior. Detailed analysis of the momentum budget reveals the extraordinary nature of the mass estimates required to explain 3I/ATLAS's behavior. The object must contain approximately 6 orders of magnitude more mass than its optical appearance suggests, a discrepancy without precedent in cometary science. This mass excess cannot be explained by conventional cometary materials, regardless of compaction or processing history. Even the densest known ices, subjected to extreme pressures, cannot achieve the bulk densities implied by the trajectory analysis, the required mass concentration approaches that found only in stellar remnants or exotic matter states. The implications extend beyond simple curiosity about an unusual object. If 3I/ATLAS truly possesses the calculated mass, it represents a fundamentally different class of interstellar object than anything previously encountered. Understanding its nature may require developing entirely new theoretical frameworks that bridge cometary science with more exotic branches of astrophysics. As this enigmatic wanderer continues its journey through our solar system, every observation adds new dimensions to the momentum paradox it presents. The comet serves as a cosmic laboratory where fundamental physics principles meet unexplained phenomena, challenging scientists to reconcile theoretical predictions with observational reality. How does one weigh an object 4 billion kilometers away, moving at speeds that dwarf our fastest spacecraft, composed of materials that existed before our solar system formed? This question lies at the heart of modern astrodynamics, where scientists must extract precise mass measurements from nothing more than points of light tracked across star fields over months and years. The challenge of determining 3I/ATLAS's mass exemplifies the sophisticated detective work that defines contemporary astronomy. Unlike laboratory experiments where objects can be handled directly, celestial mechanics relies on inferring physical properties from the subtle dance of gravitational influence and orbital dynamics observed across vast distances. Traditional methods for measuring cosmic masses exploit Newton's law of universal gravitation, which describes how massive objects attract each other with forces proportional to their masses and inversely proportional to the square of their separation. This principle enables astronomers to determine stellar masses by observing binary star orbits, planetary masses by tracking their moons, and galactic masses by measuring stellar velocities. For isolated objects like 3I/ATLAS, however, such gravitational methods prove inadequate. The comet travels alone through space, unaccompanied by orbiting companions that might reveal its gravitational influence. Scientists must therefore employ more subtle techniques that exploit the comet's response to forces acting upon it, rather than forces it exerts on others. The key insight involves recognizing that an object's acceleration under a given force inversely depends on its mass. According to Newton's second law, massive objects accelerate slowly under identical forces, while lighter objects respond more dramatically. By measuring both the forces acting on 3I/ATLAS and its resulting acceleration, astronomers can calculate its mass with remarkable precision. For comets, the relevant forces include solar gravity, which determines the basic orbital trajectory, and non-gravitational forces arising from outgassing, which cause subtle deviations from pure gravitational motion. The magnitude of these deviations provides direct information about the comet's mass, since more massive objects exhibit smaller accelerations under identical outgassing forces. Measuring these tiny accelerations requires extraordinary observational precision. The relevant changes in 3I/ATLAS's position amount to mere arcseconds across months of observation. Angular deviations, smaller than the apparent diameter of a coin, viewed from several kilometers away. Detecting such minute variations demands the combined efforts of observatories worldwide, working together to create a global monitoring network. The process begins with astrometric measurements, which determine the comet's position relative to background stars with sub-arc-second accuracy. These measurements rely on comparing the comet's location to catalogs containing the precise positions of millions of reference stars, established through decades of careful observation and analysis by missions like the European Space Agency's Gaia spacecraft. Each individual measurement contains inherent uncertainties arising from atmospheric turbulence, instrumental limitations, and random noise. However, combining hundreds or thousands of observations from multiple telescopes allows statisticians to extract meaningful signals from this observational noise. The resulting positional accuracies can approach levels of precision that seemed impossible just decades ago. Over 200 observatories worldwide have contributed measurements of 3I/ATLAS's position since its discovery. This international collaboration spans professional observatories equipped with state-of-the-art instrumentation and dedicated amateur astronomers operating from backyard installations. The diversity of observational platforms provides crucial redundancy and helps identify systematic errors that might affect individual facilities. Processing these observations requires sophisticated mathematical techniques that account for numerous sources of measurement error and systematic bias. Earth's atmosphere introduces random variations in stellar positions due to turbulent air currents. Instrumental effects cause subtle distortions in recorded star positions. The finite speed of light means that observations capture the comet's position as it existed minutes or hours earlier, depending on its distance from Earth. Orbital determination software incorporates all these factors while fitting mathematical models to the accumulated position measurements. These models describe the comet's trajectory using differential equations that account for gravitational attractions from the Sun, planets, and even large asteroids. Non-gravitational accelerations appear as additional terms in these equations, characterized by parameters that the fitting process must estimate from the data. The challenge lies in separating genuine non-gravitational accelerations from systematic errors in the observations or imperfections in the gravitational model. Spurious signals can arise from unmodeled perturbations, errors in planetary masses or positions, or instrumental systematic effects that mimic real orbital changes. Distinguishing between these possibilities requires careful analysis of the temporal evolution and directional characteristics of apparent accelerations. For 3I/ATLAS, the analysis reveals something unprecedented in cometary science: virtually no detectable non-gravitational acceleration, despite substantial outgassing activity. This result immediately implies either grossly underestimated outgassing rates or extraordinarily large mass hidden within the nucleus. Independent measurements of the outgassing rate come from spectroscopic observations that detect emission lines from sublimating materials. These measurements exploit the fact that different molecular species produce characteristic spectral signatures when excited by solar radiation. The intensity of these emission features directly relates to the number of molecules present in the coma, which in turn depends on the rate at which material sublimates from the nucleus. The James Webb Space Telescope has provided particularly precise measurements of 3I/ATLAS's outgassing rate through high-resolution infrared spectroscopy. These observations detect emission from carbon dioxide, water vapor, carbon monoxide, and other species, allowing scientists to quantify the total mass loss rate with unprecedented accuracy. Combining the measured outgassing rate with the absence of detectable non-gravitational acceleration yields mass estimates that challenge conventional understanding of cometary objects. The calculations require masses exceeding those of typical comets by factors of millions or billions, depending on the specific assumptions employed in the analysis. These extraordinary mass estimates create immediate problems for understanding the object's physical structure and composition. The required bulk density approaches, that of solid rock or metal, materials incompatible with the active outgassing behavior observed through telescopic monitoring. No known mechanism can produce such extreme density variations in objects formed through conventional cometary accretion processes. Alternative explanations focus on possible systematic errors in either the trajectory analysis or the outgassing rate measurements. Perhaps unmodeled perturbations from undiscovered solar system bodies mask subtle non-gravitational accelerations. Maybe the spectroscopic measurements significantly underestimate the true mass loss rate due to optical depth effects or unusual molecular excitation conditions. However, multiple independent measurement techniques converge on similar results, lending credibility to the basic observations. Different telescopes using different instruments and analysis methods reach consistent conclusions about both the trajectory characteristics and the outgassing activity. Such agreement argues against systematic errors affecting any single measurement approach. The statistical significance of the mass anomaly exceeds conventional thresholds for scientific discovery. The probability that measurement uncertainties could explain the observed discrepancies falls well below 1%, indicating that the effect represents genuine physical phenomenon rather than observational artifacts. Researchers have also investigated whether the comet's trajectory could be influenced by previously unrecognized forces or interactions. Perhaps electromagnetic effects associated with the solar wind or interplanetary magnetic field contribute additional accelerations that partially cancel the outgassing thrust. However, detailed calculations show that such effects remain far too small to explain the observed behavior. The mystery of 3I/ATLR's mass thus appears to represent genuine physics rather than measurement error or analytical oversights. The comet presents a puzzle that challenges fundamental assumptions about the nature and properties of interstellar objects, forcing scientists to consider possibilities that extend well beyond conventional cometary science. Picture holding two objects identical in size and shape, one carved from balsa wood, the other forged from lead. Despite their matching dimensions, the lead object weighs nearly 40 times more than its wooden counterpart. This dramatic difference illustrates how density, the fundamental relationship between mass and volume, determines the essential character of matter throughout the universe. In the realm of comets, density tells stories of formation, composition, and evolution spanning billions of years. Most comets resemble cosmic snowballs, loosely packed aggregations of ice, dust, and rocky debris that accumulated in the frigid outer reaches of planetary systems. These dirty snowballs typically exhibit densities comparable to freshly fallen snow, porous, lightweight structures held together by weak gravitational forces and molecular bonds. The European Space Agency's Rosetta mission, which spent 2 years studying comet 67P Churyumov-Gerasimenko, revealed a nucleus with bulk density of approximately 530 kilograms per cubic meter. This measurement, obtained through precise tracking of the spacecraft's orbit around the comet, confirmed theoretical predictions about the porous nature of cometary nuclei. The comet's interior contained more empty space than solid material, creating a structure resembling a cosmic pumice stone. Similar density measurements from other well-studied comets paint a consistent picture of loosely consolidated objects. Hormit 9P Tempel 1, target of NASA's Deep Impact mission, exhibited comparable bulk density despite significant differences in size and composition. These consistent results established the paradigm that comets represent primitive aggregations of materials that accreted under gentle conditions in the outer solar system. This established understanding makes 3I/ATLS particularly puzzling. If the calculated mass estimates prove correct, the comet must possess bulk density exceeding that of solid granite, a figure more than 10 times greater than typical cometary values. Such extreme density would place 3I/ATLS in an entirely different category from every other comet studied to date. The density paradox becomes even more perplexing when considering the comet's active behavior. Objects with granite-like density should consist primarily of rocky or metallic materials that lack the volatile components necessary for significant outgassing. The observed sublimation of water vapor, carbon dioxide, and other species indicates substantial ice content, yet the mass calculations suggest predominantly non-volatile composition. One possible explanation involves a structure radically different from typical comet architecture. Perhaps 3I/ATLS contains a small, extraordinarily dense core surrounded by a more conventional mantle of ice and dust. This core mantle configuration could reconcile the apparently contradictory evidence by concentrating most of the mass in a compact central region while maintaining surface volatiles responsible for observed outgassing. Theoretical models of such hybrid objects require exotic formation mechanisms that differ fundamentally from standard comet genesis. The dense core might represent a fragment of a differentiated asteroid or even more exotic material processed under extreme conditions. However, No known astrophysical processes readily explain how such massive cores could become incorporated into otherwise typical cometary structures. Alternative models invoke unusual ice phases that might achieve extraordinary density under specific conditions. Water ice exhibits numerous structural forms or polymorphs depending on temperature and pressure conditions during formation. Some of these exotic ice phases approach densities comparable to liquid water, significantly exceeding the values characteristic of ordinary hexagonal ice found in most comets. Laboratory studies have identified ice phases with densities approaching 1,500 kilograms per cubic meter under extreme pressure conditions. While such pressures rarely exist in typical comet-forming environments, unusual circumstances during formation or subsequent processing might create regions of high-density ice within cometary nuclei. However, even the densest known ice phases cannot fully account for the extreme values implied by 3I/ATLAS's trajectory analysis. Achieving the required bulk density would demand that the entire nucleus consist of the densest possible materials, leaving little room for the conventional ices responsible for observed outgassing activity. More exotic possibilities involve materials rarely considered in cometary science. Certain metallic glasses, formed through rapid cooling of molten metals, can achieve extremely high density while retaining significant volatile content. Such materials might result from unusual processing in stellar environments or during high-energy events like supernovae explosions. The concept of metallic hydrogen, predicted under extreme pressure conditions, represents another theoretical possibility. This exotic phase of matter might achieve densities several times that of liquid water, while potentially retaining capacity for volatile behavior under appropriate conditions. However, the stability of metallic hydrogen under the temperature and pressure conditions relevant to 3I/ATLAs remains highly uncertain. Another approach to the density dilemma focuses on questioning the size estimates used in density calculations. If 3I/ATLAs proves significantly larger than current optical measurements suggest, the required bulk density would decrease correspondingly. However, this possibility faces its own challenges, since larger size estimates must reconcile with brightness observations that constrain the object's light-reflecting surface area. The distinction between nucleus size and total comet size introduces additional complexity to density calculations. Active comets develop extensive comas of sublimated gas and entrained dust that can obscure the underlying nucleus from direct observation. Current size estimates for 3I/ATLAs rely primarily on brightness measurements that may reflect contributions from both nucleus and coma. Sophisticated models attempt to separate nuclear brightness from coma contributions using theoretical understanding of dust scattering and gas emission processes. These models suggest nuclear radii ranging from several hundred meters to a few kilometers, depending on assumptions about surface composition and activity levels. However, uncertainties in these assumptions propagate into corresponding uncertainties in density estimates. The temporal evolution of 3I/ATLAs brightness provides additional constraints on nucleus to coma brightness ratios. Observations reveal relatively stable brightness levels over periods of months, suggesting either steady nucleus activity or coma contributions that maintain constant proportions. Such stability argues against dramatic changes in the relative contributions of different brightness sources. Polarimetry measurements offer another approach to constraining the physical properties of cometary nuclei. The polarization characteristics of reflected sunlight depend sensitively on the size distribution, composition, and packing density of scattering particles. For 3I/ATLAs, preliminary polarimetry studies suggest unusual scattering properties that differ from typical comets. These polarization anomalies might indicate surface materials with optical properties distinct from conventional cometary dust. Perhaps the nucleus surface consists of materials processed under conditions that create unusual grain sizes, shapes, or compositions. Such processing could result from the extreme conditions associated with interstellar travel or formation in environments unlike those characteristic of our solar system. The relationship between surface properties and bulk density remains complex and poorly understood for cometary objects. Surface materials represent only a tiny fraction of total mass, yet they control optical observability and outgassing behavior. Understanding this relationship proves crucial for interpreting density measurements based on trajectory analysis. As observations continue, Each new measurement adds constraints to the density puzzle presented by 3I/Atlas. The comet challenges fundamental assumptions about the relationship between composition, structure, and observable properties that define our understanding of small bodies in space. Resolving this challenge may require developing entirely new frameworks for understanding how matter behaves under the extreme conditions that characterize interstellar environments. Imagine discovering a diamond, the size of a basketball, lying on a public beach after finding only 2 tiny pebbles during years of searching. The improbability of such a find would immediately raise questions about the underlying processes that distribute precious stones along shorelines. This analogy captures the statistical puzzle that 3I/Atlas presents to astronomers attempting to understand the population of objects wandering between the stars. Our galaxy contains countless objects ejected from planetary systems throughout cosmic history. Gravitational interactions during early system formation scatter asteroids, comets, and even planets into interstellar space, where they drift for billions of years before occasionally encountering other stellar systems. These interstellar wanderers represent fossil remnants of planetary formation processes, carrying information about conditions in stellar nurseries throughout galactic evolution. The discovery of any interstellar object requires extraordinary timing and observational capabilities. Such visitors spend only months or years crossing our solar system, appearing as faint points of light against star fields containing millions of objects. Detection depends on recognizing subtle orbital characteristics that distinguish interstellar trajectories from the countless asteroids and comets gravitationally bound to our Sun. Statistical models predict the encounter rates for interstellar objects based on their estimated abundance in galactic space and typical relative velocities during solar system encounters. These models suggest that smaller objects should vastly outnumber larger ones, following power law distributions characteristic of collisional fragmentation processes that break apart larger bodies over cosmic time. The size distribution of objects in our own asteroid belt exemplifies this pattern. For every asteroid larger than 100 kilometers in diameter, approximately 1,000 asteroids exist between 10 and 100 kilometers across. This ratio continues to smaller sizes, with millions of objects in the 1 to 10 kilometer range for each large asteroid. Similar scaling relationships should govern interstellar object populations, since the same physical processes, collisional fragmentation, gravitational disruption, and thermal processing, affect material in both bound and unbound orbital configurations. The fundamental physics of how objects break apart and redistribute their mass remains unchanged, whether the fragments orbit a star or drift through interstellar space. Based on these scaling arguments, discovering 3I/Atlas with its estimated mass of tens of billions of tons should occur only after detecting approximately 100,000 smaller interstellar objects. The mathematical relationship follows directly from the steep size distribution observed in asteroid populations and confirmed in theoretical models of collisional evolution. Yet 3I/Atlas arrived as merely the third confirmed interstellar visitor, following 1I/Oumuamua and 2I/Borisov. This sequence violates statistical expectations by enormous margins, suggesting either fundamental errors in population models or extraordinary circumstances affecting the specific objects we have detected. The problem becomes even more acute when considering detection capabilities and observational selection effects. Current surveys find small objects more easily than large ones when brightness depends primarily on reflected sunlight. Smaller objects present larger surface area to mass ratios, making them inherently brighter per unit mass than compact, dense objects of equivalent total mass. These observational biases should strongly favor detection of numerous small interstellar objects before any massive ones become visible. The fact that we discovered such an apparently massive object among our first few detections challenges both population statistics and detection probability calculations. One potential explanation involves invoking fundamentally different size distributions for interstellar objects compared to gravitationally bound populations. Perhaps the processes that eject objects from planetary systems preferentially affect larger bodies, creating interstellar populations dominated by massive objects rather than small fragments. However, theoretical studies of planetary system evolution suggest the opposite trend. Gravitational scattering events more easily eject smaller objects, since they possess lower binding energies and respond more dramatically to perturbations from massive planets. Large objects require more extreme encounters to achieve escape velocities, making them statistically less likely to enter interstellar space. Alternatively, perhaps interstellar objects undergo processing during their billions of years of galactic wandering that systematically increases their masses. Accretion of interstellar dust and gas might gradually build up surface layers, or gravitational focusing effects could concentrate smaller objects into larger aggregates through rare collision events. Such processing mechanisms face significant physical constraints. The extremely low density of interstellar medium limits accretion rates to negligible levels over relevant timescales. Collision probabilities in the vast emptiness between stars remain vanishingly small, making aggregate formation through random encounters highly implausible. Another possibility involves selection effects related to the detection methods used to identify interstellar objects. Perhaps our current survey techniques systematically miss certain classes of small objects, while remaining sensitive to specific types of massive ones. This bias could create apparent population distributions that differ dramatically from true underlying abundances. However, detailed analysis of survey sensitivities suggests that current detection methods should readily identify small interstellar objects if they exist in predicted numbers. The surveys that discovered 3I/ATLAS routinely detect much smaller asteroids and comets within our solar system, indicating adequate sensitivity for interstellar objects of comparable size. The temporal aspect of the discovery sequence adds another layer to the statistical puzzle. If massive interstellar objects represent rare tail events in the size distribution, their detection should correlate with survey duration and depth. Finding such an object early in the survey history suggests either exceptional luck or systematic underestimation of large object abundance. Calculating the precise probability of detecting 3I/ATLAS when we did requires detailed modeling of survey parameters, detection thresholds, and assumed population characteristics. These calculations consistently yield probabilities well below 1%, indicating that the observation represents either extraordinary fortune or fundamental misunderstanding of the underlying physics. The implications extend beyond academic interest in population statistics. Understanding the true abundance and size distribution of interstellar objects affects estimates of their role in galactic chemical evolution, panspermia mechanisms, and potential hazards to spacecraft exploring the outer solar system. If massive interstellar objects prove more common than current models predict, they might play significant roles in transporting materials between stellar systems throughout galactic history. Such transport could affect the chemical evolution of galaxies by redistributing processed materials from older stellar populations to younger systems. Conversely, if 3I/ATLAS represents an exceptionally rare object, its detection suggests that current survey capabilities have reached the threshold where such rare events become observable. Future surveys with improved sensitivity might reveal whether large interstellar objects represent genuine statistical anomalies or the first glimpses of previously hidden populations. The mass budget problem presented by 3I/ATLAS thus touches fundamental questions about galactic evolution, planetary system formation, and the processes that shape small body populations throughout cosmic history. Resolving this puzzle may require rethinking basic assumptions about how matter distributes itself across the scales ranging from individual objects to entire galaxies. As surveys continue and detection capabilities improve, the statistical context surrounding 3I/ATLAS will become clearer. Each new interstellar object discovery will either reinforce the apparent anomaly or reveal it as the first member of a previously unrecognized population of cosmic wanderers, carrying masses that challenge our understanding of how the universe distributes matter across interstellar space. Consider an iceberg floating in Arctic waters, revealing only its modest tip while concealing a massive foundation beneath the surface. This familiar image captures one potential explanation for 3I/ATLAS's mysterious behavior. Perhaps the comet's visible activity represents merely the outermost layer of a vastly more complex internal structure that hides extraordinary mass concentrations within. The concept of hidden architecture in cometary nuclei challenges traditional models that assume relatively homogeneous composition throughout these objects. Most theoretical frameworks describe comets as loosely consolidated mixtures of ice, dust, and rocky material distributed fairly uniformly within porous rubble pile structures. However, more sophisticated formation scenarios allow for dramatic internal heterogeneity that could concentrate mass in unexpected ways. Differentiation processes, well studied in asteroids and planets, might also affect larger cometary bodies under specific conditions. If 3I/Atlas formed as a much larger object that subsequently experienced heating from radioactive decay or other energy sources, denser materials could have migrated inward, while volatile components remained concentrated near the surface. Such differentiation requires sufficient mass and internal energy to drive convective or gravitational settling processes over extended periods. The timescales involved span millions to billions of years, easily accommodated within the likely age of an interstellar object that predates our solar system's formation. Heat sources could include radioactive decay of short-lived isotopes, electromagnetic induction in strong magnetic fields, or thermal energy from high-velocity impacts. The resulting structure might resemble a cosmic onion, with layers of progressively denser material toward the center. Surface layers would retain the volatile components responsible for observed outgassing activity, while deeper regions could contain materials ranging from hydrated minerals to pure metals. The bulk density would depend on the relative proportions and densities of these different layers. Observational evidence for such stratified structures remains limited in cometary science, partly due to the difficulty of probing internal compositions using remote sensing techniques. However, variations in outgassing patterns, surface composition, and mechanical properties observed in well-studied comets hint at internal complexity that simple homogeneous models cannot explain. The Deep Impact mission, which excavated material from Comet 9P Tempel 1, revealed subsurface compositions that differed significantly from surface materials. The excavated debris contained higher proportions of fine dust and different ice-to-rock ratios than expected, based on surface observations alone. These findings suggest that even relatively small comets can exhibit substantial internal stratification. For 3I/ATLS, the required mass concentration implies core densities approaching those of solid metal or compressed rock. Achieving such densities within cometary objects demands either exotic formation conditions or subsequent processing that fundamentally alters the original structure. The core might consist of materials rarely considered in conventional cometary models. One possibility involves the incorporation of fragments from disrupted asteroids or even planetary cores during the comet's formation or subsequent evolution. Gravitational capture of dense objects could embed high-mass cores within otherwise typical cometary matrices. Such capture events might occur during close encounters with massive bodies or through three-body interactions in crowded stellar environments. Alternatively, the core might consist of materials formed under extreme pressure conditions, either in the parent system's deep interior or during high-energy events like stellar collisions or supernova explosions. These materials could include exotic ice phases, metallic glasses, or even more speculative forms of condensed matter that remain stable under interstellar conditions. The question of how such dense cores remain thermally and mechanically stable within active cometary nuclei presents additional challenges. Dense materials typically possess higher thermal conductivity than the porous ice dust mixtures characteristic of comet mantles. This enhanced heat transport could affect outgassing patterns and internal temperature distributions in complex ways. Thermal modeling of stratified cometary structures reveals intricate feedback mechanisms between internal heat sources, thermal conductivity variations, and volatile sublimation rates. Dense cores might act as thermal reservoirs that moderate temperature fluctuations, or conversely, as heat sinks that affect the timing and intensity of outgassing activity. The mechanical stability of such hybrid structures depends on the strength and cohesion of materials at interfaces between layers of vastly different density. Thermal expansion and contraction cycles, internal pressure variations, and rotational stresses could potentially disrupt layered configurations over geological timescales. Observational signatures of internal stratification might include unusual patterns in outgassing activity, unexpected variations in surface composition, or anomalous responses to external heating. For 3I/Atlas, the absence of detectable non-gravitational acceleration, despite substantial mass loss, could itself represent evidence for extreme mass concentration that minimizes the dynamical effects of outgassing forces. Detailed spectroscopic analysis of the comet's coma might reveal chemical signatures of materials originating from different depths within the nucleus. Variations in isotopic ratios, molecular species, or dust properties could indicate the presence of distinct compositional reservoirs that contribute differentially to the observable outgassing. The dust-to-gas ratio in cometary cometae provides another diagnostic tool for internal structure. Objects with dense cores and volatile mantles might exhibit distinctive temporal variations in dust production as subsurface materials become exposed through surface erosion processes. These variations could manifest as changes in brightness, color, or polarization properties over observational timescales. High-resolution imaging of 3I/Atlas remains challenging due to its distance and relatively small apparent size. However, future observational campaigns using adaptive optics or space-based telescopes might resolve surface features that provide clues about internal architecture. Variations in surface brightness, terrain morphology, or activity patterns could reveal the locations of compositional boundaries. The gravitational field generated by a stratified nucleus would differ subtly from that of a homogeneous object with identical total mass. These differences, while tiny, might be detectable through precise tracking of dust particles or small debris in the comet's immediate vicinity. Such measurements would require extraordinary observational precision, but could provide direct evidence for internal mass concentrations. Alternative architectures for hiding mass within 3I/Atlas might involve hollow or partially hollow structures that concentrate material in outer shells while maintaining low overall density. Such configurations could arise from internal melting and drainage processes that redistribute material during periods of intense heating, or from impact excavation that creates internal void spaces. The engineering challenges associated with maintaining structural integrity in hollow cometary objects suggest that such architectures would be inherently unstable over cosmic timescales. However, specific configurations might achieve temporary stability through rotational support or internal pressure effects. As observational capabilities continue advancing, the mystery of 3I/Atlas's internal architecture will gradually yield to increasingly sophisticated analysis techniques. Each new measurement provides constraints on possible structural models, slowly narrowing the range of scenarios that can explain the comet's extraordinary behavior while maintaining consistency with observed properties. The hidden architecture hypothesis represents just one approach to explaining 3I/Atlas's mass anomaly, but it illustrates the creative theoretical thinking required to reconcile apparently contradictory observations. Understanding the true nature of this cosmic visitor may ultimately require abandoning conventional assumptions about how matter organizes itself in the extreme environments that characterize interstellar space. Three fundamental observations about 3I/Atlas create a puzzle that challenges our understanding of how physics operates in the cosmos. The comet loses approximately 150 kilograms of material every second through sublimation. It exhibits active outgassing visible to the most sophisticated telescopes in human history, yet it travels through space as though these massive gas emissions exert no influence whatsoever on its trajectory. This trinity of facts represents more than an academic curiosity. It strikes at the heart of conservation principles that govern all motion in the universe. Every rocket engine, every jet aircraft, every balloon floating in Earth's atmosphere operates according to the same fundamental relationship between mass expulsion and momentum change that should affect 3I/Atlas. The James Webb Space Telescope's infrared spectroscopy capabilities have revolutionized our ability to measure outgassing rates from distant comets. Unlike visible light observations that can be confused by dust scattering, infrared measurements detect direct emission from gas molecules heated by solar radiation. These spectral lines provide unambiguous signatures of specific chemical species and their abundance in cometary cometae. For 3I/Atlas, Webb's measurements reveal emission lines from water vapor, carbon dioxide, carbon monoxide, and several other molecular species characteristic of cometary outgassing. The intensity of these lines, combined with theoretical models of molecular excitation and emission, yields precise estimates of the mass loss rate that agree remarkably well with independent measurements using other techniques. The consistency of these measurements across different observational methods strengthens confidence in the basic outgassing rate determination. Ground-based radio telescopes detect molecular transitions at millimeter wavelengths, Optical telescopes measure brightness variations associated with dust production, and space-based ultraviolet instruments observe dissociation products from parent molecules. All approaches converge on mass loss rates near 150 kilograms per second. Such substantial outgassing should generate measurable thrust through the rocket principle that governs all reaction-based propulsion systems. Gas molecules escaping from the nucleus carry momentum proportional to their mass and velocity. Conservation of momentum demands that the nucleus recoil in the opposite direction with equal momentum, creating a net force that gradually alters the comet's trajectory. The magnitude of this force depends on several factors, including the outgassing rate, the average molecular weight of escaping species, the gas temperature that determines molecular velocities, and the efficiency with which momentum transfers from gas to nucleus. For typical comets, these parameters combine to produce forces ranging from a few newtons to several thousand newtons, depending on the comet's activity level and size. Even modest forces of a few newtons, acting continuously over months or years, accumulate to produce readily detectable changes in orbital elements. The acceleration imparted to the nucleus equals the thrust force divided by the nucleus mass, so lighter objects respond more dramatically to identical outgassing forces. This relationship provides the basis for using trajectory analysis to determine cometary masses. For 3I/8LS, the expected acceleration based on observed outgassing rates should be easily detectable using current astrometric techniques. The predicted trajectory deviations exceed measurement uncertainties by factors of 10 to 100, making non-detection particularly puzzling rather than merely surprising. The temporal characteristics of the outgassing provide additional constraints on possible explanations for the trajectory anomaly. Spectroscopic monitoring reveals relatively steady emission over periods of months, suggesting stable sublimation processes rather than sporadic or highly variable activity. Such consistency argues against explanations involving unusual asymmetries or directionality effects that might cancel out thrust components. Gas velocity measurements from Doppler-shifted spectral lines indicate expansion speeds typical of thermal sublimation processes. The observed velocities match theoretical predictions based on solar heating and molecular properties, confirming that the outgassing occurs through conventional mechanisms rather than exotic processes that might affect momentum transfer differently. The composition of escaping gases also follows patterns expected from solar heating of typical cometary materials. Water vapor dominates at moderate heliocentric distances, while carbon dioxide becomes increasingly prominent at larger solar distances where water ice remains stable. This compositional evolution matches theoretical models of preferential sublimation from multi-component ice mixtures. However, the absence of non-gravitational acceleration despite this apparently normal outgassing behavior implies either fundamental errors in trajectory analysis or extraordinary physical conditions that violate standard momentum conservation principles. Neither possibility offers comfortable explanations within current theoretical frameworks. One potential resolution involves invoking perfect symmetry in the outgassing pattern that produces zero net thrust despite substantial mass loss. If gas emission occurs uniformly from all surface locations with identical velocities and rates, the individual thrust components would cancel exactly, producing no net force on the nucleus. However, achieving such perfect symmetry requires extraordinary conditions, rarely if ever observed in real cometary objects. Natural comets exhibit irregular shapes, heterogeneous surface compositions, and variable thermal properties that create asymmetric outgassing patterns. Seasonal effects associated with nuclear rotation expose different surface regions to solar heating at different times, while topographical features like craters or ridges create preferential emission sites that break spherical symmetry. Even if some mechanism maintained perfect outgassing symmetry, maintaining such delicate balance over extended periods would require extraordinary stability in surface properties and heating conditions. Small perturbations from dust impacts, thermal cycling, or surface evolution would gradually disrupt the symmetry and restore measurable non-gravitational accelerations. Alternative explanations focus on the possibility that momentum transfer between outgassing and nucleus occurs with unusual efficiency or through mechanisms that differ from conventional models. Perhaps the internal structure of 3I/8LS includes cavities or channels that redirect gas flow in ways that minimize net thrust production. Theoretical studies of gas flow through porous media suggest that complex internal geometries can indeed affect momentum transfer efficiency. Gas expanding through interconnected pore networks experiences pressure, forces, and viscous interactions that can redirect flow patterns and modify thrust characteristics. However, even highly tortuous flow paths typically retain substantial momentum coupling to the solid matrix. The scale of momentum decoupling required to explain 3I/8LA's behavior exceeds anything predicted by current models of gas-solid interactions. Reducing the effective thrust to unmeasurable levels would require momentum transfer efficiencies near zero, values incompatible with any plausible physical mechanism. Another approach considers whether systematic errors in outgassing rate measurements might significantly underestimate the true mass loss. Perhaps optical depth effects in dense regions of the coma prevent accurate census of all sublimating material, or unusual molecular excitation conditions affect the relationship between spectral line intensity and gas production rates. However, multiple independent measurement techniques yield consistent results for the outgassing rate, arguing against systematic errors that would affect only specific observational methods. The convergence of different approaches suggests that the basic mass loss measurements provide reliable estimates of the true sublimation activity. The outgassing paradox thus appears to represent genuine physical phenomenon rather than observational artifacts or analytical errors. This conclusion forces consideration of more radical explanations that challenge fundamental assumptions about momentum conservation, internal structure, or the nature of 3I/8LS itself. Perhaps the comet contains mechanisms for momentum storage and release that operate on timescales longer than current observational periods. Internal structural changes, phase transitions, or electromagnetic effects might temporarily store momentum imparted by outgassing before releasing it through different channels that do not affect the overall trajectory. Such exotic mechanisms remain purely speculative without observational evidence or theoretical frameworks to support their operation. Nevertheless, the extraordinary nature of 3I/8LS's behavior may require equally extraordinary explanations that extend well beyond conventional cometary science into realms of physics where our understanding remains incomplete. Every massive object in the universe leaves subtle signatures of its presence through gravitational influence that extends infinitely through space, weakening with distance but never completely disappearing. These gravitational fingerprints provide astronomers with powerful tools for detecting and characterizing objects that might otherwise remain invisible, from black holes consuming matter to dark matter halos surrounding galaxies. If 3I/8LAS truly possesses the extraordinary mass suggested by trajectory analysis, its gravitational influence should extend throughout the local space environment, affecting the motion of dust particles, small debris, and even spacecraft operating in the outer solar system. However, detecting these subtle effects requires observational precision that pushes current technology to its absolute limits. The gravitational field surrounding any spherically symmetric massive object follows Newton's inverse square law, diminishing rapidly with increasing distance from the source. For an object with the mass estimated for 3I/8LAs, the gravitational acceleration at distances of several thousand kilometers approaches that experienced by satellites orbiting Earth at altitude. Such fields should produce measurable effects on appropriately sensitive test particles. Natural test particles exist throughout the solar system in the form of dust grains, small meteoroids, and debris associated with cometary activity. These particles, with masses ranging from micrograms to grams, respond sensitively to weak gravitational perturbations that would barely affect larger objects. Their orbital evolution over time could potentially reveal the presence of massive objects through accumulated trajectory deviations. However, detecting gravitational perturbations from 3I/8LAS faces significant observational challenges. The relevant test particles remain invisible to direct observation, requiring indirect detection methods based on their effects on observable phenomena. Dust impacts on spacecraft, variations in zodiacal light intensity, or changes in debris density distributions might provide accessible signatures of gravitational focusing effects. Spacecraft operating in the outer solar system offer the most precise platforms for detecting weak gravitational anomalies. These robotic explorers carry sophisticated navigation systems capable of measuring position and velocity changes with extraordinary accuracy. Unexpected trajectory deviations could reveal the gravitational influence of previously unrecognized massive objects. The Voyager spacecraft, despite their advanced age, continue providing position data accurate to within several kilometers across distances of billions of kilometers from Earth. This precision rivals that achieved by the most sophisticated Earth-orbiting satellites, demonstrating the feasibility of detecting gravitational anomalies in deep space environments. New Horizons, the spacecraft that flew past Pluto and continues toward interstellar space, represents an even more sensitive probe of gravitational fields in the outer solar system. Its trajectory, monitored continuously through radio communications with Earth, could potentially reveal gravitational influences from massive interstellar objects passing through our solar system. However, disentangling genuine gravitational perturbations from other effects affecting spacecraft trajectories requires careful analysis of multiple potential sources of trajectory deviation: solar radiation pressure, thermal emission from the spacecraft itself, gas leaks from propulsion systems, and gravitational influences from known solar system bodies all contribute to spacecraft motion in ways that could mask or mimic gravitational signals from 3I/ATLAS. The timing of 3I/ATLAS's passage through our solar system provides a natural experiment for testing gravitational influence hypotheses. If the comet possesses extraordinary mass, spacecraft trajectories should show systematic deviations that correlate temporally and geometrically with the comet's position. The magnitude and direction of these deviations would depend on the spacecraft's distance from 3I/ATLAS and the geometry of their relative positions. Theoretical calculations suggest that gravitational perturbations from a 33 billion-ton object could produce trajectory deviations on the order of several meters to several kilometers for spacecraft operating at distances of millions of kilometers. These deviations accumulate over time, creating potentially detectable signals that grow stronger with extended observation periods. The gravitational influence extends beyond individual spacecraft to affect the broader debris environment throughout the outer solar system. Dust particles and small meteoroids experience gravitational focusing effects that could alter their spatial distribution and velocity patterns in ways that remain observable long after 3I/ATLAS passes through the region. Gravitational focusing occurs when the gravitational field of a massive object deflects the trajectories of passing particles, concentrating them into higher density regions downstream from the gravitational source. This phenomenon, well studied in the context of planetary and stellar gravitational lensing, could create detectable variations in debris density that persist for months or years after the gravitational source moves on. The Kuiper Belt, home to countless small objects orbiting beyond Neptune, provides a natural laboratory for studying gravitational perturbation effects. If 3I/ATLAS possesses sufficient mass, its passage through this region should leave lasting signatures in the orbital distribution of Kuiper Belt objects that could be detected through systematic survey observations. Current sky surveys like the Large Synoptic Survey Telescope (LSST) will eventually catalogue the positions and motions of millions of objects in the outer solar system with unprecedented precision. These datasets will enable statistical analyses that could reveal subtle gravitational perturbation signatures associated with the passage of massive interstellar objects. However, the gravitational influence of 3I/ATLAS must compete with numerous other sources of orbital perturbation affecting small bodies in the outer solar system. Gravitational perturbations from the giant planets, the galactic tidal field, passing stars, and even molecular clouds all contribute to the long-term orbital evolution of these objects. Separating the specific signature of 3I/ATLAS's gravitational influence from this complex background requires sophisticated statistical analysis techniques that can identify correlated patterns in orbital changes among multiple objects. The signal-to-noise ratio for such analyses depends critically on both the true mass of 3I/ATLAS and the precision of orbital measurements for test objects. Alternative approaches to detecting gravitational signatures focus on electromagnetic phenomena that might be affected by strong gravitational fields. The propagation of radio signals through space experiences subtle deflection in the presence of massive objects, creating arrival time delays that could potentially be measured using pulsar timing or spacecraft communication signals. Pulsar timing arrays, designed primarily to detect gravitational waves, achieve timing precision approaching nanosecond accuracy over periods of years. Such precision might be adequate to detect gravitational light-bending effects associated with very massive objects passing through the solar system, though the required signal-to-noise ratios remain challenging to achieve. The search for gravitational fingerprints from 3I/ATLAS thus represents an ongoing observational challenge that will likely extend well beyond the comet's departure from our solar system. The accumulated effects of gravitational perturbations continue evolving long after the source has moved on, providing extended opportunities to detect evidence for extraordinary mass through careful analysis of debris motion and spacecraft trajectories. As observational capabilities continue improving and datasets accumulate over longer time periods, the prospects for detecting gravitational signatures from massive interstellar objects will correspondingly improve. 3I/ATLAS serves as a test case for developing the observational techniques and analysis methods needed to characterize similar objects that may visit our solar system in the future. The absence or presence of detectable gravitational fingerprints will ultimately provide crucial constraints on the true mass of this enigmatic visitor. If no such signatures emerge despite careful searching, it would suggest that current mass estimates significantly overestimate 3I/ATLAS's true mass, forcing reconsideration of the fundamental assumptions underlying trajectory analysis methods. Deep within stellar cores, where temperatures exceed 10 million degrees and pressures crush matter to densities unimaginable on Earth, nuclear fusion forges elements that will eventually find their way into planets, asteroids, and comets throughout the galaxy. Yet even these extreme stellar environments may prove insufficient to explain the exotic materials that could account for 3I/ATLAS's extraordinary mass anomaly. The quest to understand what 3I/ATLAS might be made of takes us into realms where conventional chemistry gives way to more exotic forms of matter that exist only under the most extreme conditions in nature. If the mass calculations prove correct, this interstellar visitor must contain materials with densities that challenge our understanding of how atoms organize themselves into stable structures. Water ice, the most abundant volatile component in typical comets, exists in multiple crystalline forms depending on temperature and pressure conditions during formation. Under the low-pressure, low-temperature conditions characteristic of comet-forming regions, water molecules arrange themselves into the familiar hexagonal crystal structure that creates snowflakes and fills our freezers. This ordinary ice exhibits densities near 920 kilograms per cubic meter. However, subjecting water to extreme pressures generates entirely different crystalline arrangements with dramatically higher densities. Ice, too, formed under pressures exceeding 3,000 atmospheres, achieves densities approaching 1,300 kilograms per cubic meter. Even denser phases like Ice 7 can exceed 1,500 kilograms per cubic meter under the crushing pressures found deep within giant planets. These high-pressure ice phases might form during catastrophic events that compress cometary material far beyond ordinary conditions. Stellar collisions, supernova shockwaves, or encounters with black holes could generate the extreme pressures necessary to create such exotic ices within otherwise conventional cometary bodies. Yet even the densest known ice phases fall short of the extreme values required to explain 3I/ATLAS's behavior. Achieving the necessary bulk density would require materials more exotic than anything found in typical planetary environments, pushing into regimes where quantum mechanical effects begin dominating the properties of matter itself. Metallic hydrogen represents one theoretical possibility for achieving extraordinary density while maintaining some volatile characteristics. Under sufficiently extreme pressure, hydrogen atoms lose their individual electron clouds and form a metallic lattice with properties resembling both conventional metals and compressed gases. The density of metallic hydrogen could reach several thousand kilograms per cubic meter, while potentially retaining capacity for sublimation under appropriate conditions. Laboratory efforts to create stable metallic hydrogen have achieved only limited success, producing tiny quantities that remain stable for brief periods under extraordinary pressure conditions. The existence of naturally occurring metallic hydrogen in cosmic environments remains speculative, though theoretical models suggest it might form in the cores of gas giant planets or during stellar formation processes. Alternatively, 3I/ATLAS might contain materials processed during nucleosynthesis events that create elements heavier than those typically found in comets. Neutron star collisions, responsible for creating gold, platinum, and other heavy elements, also generate ultra-dense nuclear matter that temporarily achieves densities millions of times greater than ordinary solids. While such extreme nuclear matter cannot remain stable under normal conditions, intermediate density materials might form during the cooling and expansion phases following neutron star mergers. These materials could incorporate heavy elements compressed into crystal lattices with densities far exceeding those of ordinary rocks or metals. The concept of strange matter, composed of quarks rather than conventional protons and neutrons, represents an even more exotic possibility. Strange matter could theoretically achieve densities approaching those of atomic nuclei while remaining stable under conditions encountered in interstellar space. However, the existence of stable strange matter remains highly speculative, with no confirmed observations despite extensive theoretical interest. Carbon, abundant in comets and throughout the universe, forms crystalline structures with remarkable diversity depending on pressure and temperature conditions during formation. Diamond, the high-pressure form of carbon, achieves densities exceeding 3,000 kilograms per cubic meter. Even denser carbon phases might exist under the extreme conditions associated with stellar formation or interstellar processing. Lonsdaleite, a rare form of diamond created by meteorite impacts, exhibits density and hardness properties that exceed those of ordinary diamond. This material forms when carbon-rich meteorites experience the extreme shock conditions associated with high-velocity impacts. Similar shock processing might occur during interstellar travel as objects encounter debris or extreme electromagnetic environments. Fullerenes and carbon nanotubes represent other forms of carbon with unique properties that might contribute to unusual density characteristics. These materials can trap other atoms or molecules within their cage-like structures, potentially creating composite materials with densities and sublimation properties unlike anything found in conventional minerals. The role of magnetic fields in creating unusual material properties deserves consideration given the strong magnetic environments that might exist during interstellar travel. Intense magnetic fields can alter the electronic structure of atoms and molecules, potentially stabilizing unusual crystalline arrangements or creating magnetic order that affects bulk density. Ferromagnetic materials like iron and nickel can achieve higher packing densities when their magnetic moments align in strong external fields. While this effect typically produces modest density increases, the extreme magnetic environments associated with neutron stars or stellar magnetic fields could potentially create more dramatic structural modifications. Superconducting materials, which exhibit zero electrical resistance below critical temperatures, also display unusual magnetic properties that might affect their structural characteristics. Type II superconductors can trap magnetic flux in quantized vortices, potentially creating internal structures with densities that differ from their non-superconducting counterparts. The possibility that 3I/Atlas contains artificially manufactured materials cannot be dismissed entirely, though it requires invoking technological capabilities far beyond current human achievements. Advanced materials science might develop techniques for creating ultra-dense materials with properties optimized for specific applications like interstellar travel. Such materials might incorporate engineered nanostructures, controlled porosity distributions, or phase change capabilities that create variable density distributions responding to external conditions. However, the stability of such artificial materials over billions of years of interstellar exposure would require engineering principles far beyond current technological horizons. Amorphous materials, lacking the regular crystalline structure of conventional solids, might achieve unusual density characteristics through disordered atomic arrangements that maximize packing efficiency. Metallic glasses, formed by rapid cooling of molten metals, can exhibit densities that exceed those of their crystalline counterparts while maintaining unique mechanical and chemical properties. The formation of such amorphous phases in interstellar environments might occur through radiation processing, thermal cycling, or mechanical deformation during billions of years of galactic wandering. These processes could gradually modify conventional crystalline materials into amorphous phases with altered density characteristics. As 3I/Atlas continues its journey through our solar system, spectroscopic analysis of its coma and surface materials may eventually provide clues about its composition. Each molecular species detected in the outgassing provides constraints on the materials present within the nucleus, gradually building a picture of the exotic chemistry that might explain its mysterious mass. The material mystery of 3I/ATLAS thus spans scales from nuclear physics to stellar evolution, challenging our understanding of how matter behaves under the extreme conditions that characterize interstellar space. Solving this puzzle may require insights from multiple fields of physics and chemistry, ultimately expanding our knowledge of the exotic forms that matter can assume throughout the universe. The story of 3I/ATLAS extends far beyond the puzzle of a single massive object wandering through our solar system. This enigmatic visitor carries implications that ripple through multiple branches of astronomy, challenging fundamental assumptions about planetary formation, stellar evolution, and the very nature of matter distribution throughout our galaxy. If the mass estimates for 3I/ATLAS prove accurate, they suggest that our understanding of how objects form and evolve in interstellar environments may be profoundly incomplete. The discovery forces astronomers to confront the possibility that processes operating in the vast spaces between stars can create objects with properties unlike anything found in our own solar system. Traditional models of comet formation rely on gentle accretion processes occurring in the cold, low-density environments characteristic of planetary system peripheries. These models successfully explain the properties of countless comets observed within our solar system, from small periodic visitors to the largest known cometary nuclei. However, they provide no mechanism for creating objects with the extreme mass-to-size ratios implied by 3I/ATLAS's behavior. The existence of such anomalous objects might indicate that alternative formation pathways operate in interstellar space, where conditions differ dramatically from those found in gravitationally bound planetary systems. The interstellar medium, while extremely tenuous by terrestrial standards, extends across volumes so vast that total mass accumulation over billions of years might achieve levels impossible within individual planetary systems. Magnetic fields threading interstellar space could play crucial roles in concentrating matter and enabling accretion processes that differ fundamentally from gravitational assembly mechanisms. These fields, generated by galactic rotation and stellar activity, create complex structures that can channel gas and dust flows across enormous distances, potentially building massive objects through mechanisms that remain poorly understood. The implications extend to our understanding of galactic chemical evolution, the processes by which elements created in stellar cores spread throughout galactic environments and incorporate into new generations of stars and planets. If massive interstellar objects like 3I/ATLAS exist in significant numbers, they represent previously unrecognized reservoirs of processed material that could affect chemical evolution on galactic scales. These wandering repositories might transport materials between widely separated stellar systems, creating chemical mixing processes that operate over timescales of billions of years. Such transport could help explain observed uniformity and elemental abundance patterns across different galactic regions, complementing the mixing processes associated with stellar winds and galactic rotation. The detection of 3I/ATLAS also raises questions about the population statistics that govern interstellar objects throughout our galaxy. Current theoretical models predict size and mass distributions based on the assumption that interstellar objects represent ejected debris from planetary systems. These models successfully predict the discovery rates for objects like 1I/Oumuamua and 2I/Borisov, which exhibit properties consistent with their solar system counterparts. However, 3I/ATLAS appears to violate these statistical predictions in fundamental ways, suggesting that additional populations of interstellar objects might exist with characteristics that differ dramatically from typical planetary system debris. Understanding these populations requires developing new theoretical frameworks that account for formation and evolution processes operating in interstellar environments. The observational challenges associated with characterizing 3I/ATLAS highlight limitations in current astronomical capabilities that may prevent recognition of similar objects. Perhaps numerous massive interstellar visitors have passed through our solar system without detection, either because they remained too distant from the Sun to develop visible comet, or because their unusual properties rendered them invisible to conventional survey techniques. Future observational programs designed to detect and characterize interstellar objects will need to account for the possibility that such visitors might exhibit properties unlike anything found within our own solar system. This requirement may drive development of new detection strategies and analysis techniques, specifically optimized for identifying anomalous objects with unusual mass-to-brightness ratios. The trajectory analysis techniques developed for studying 3I/ATLAS will likely find broader applications in characterizing other unusual objects discovered in future surveys. The methods for extracting mass information from non-gravitational acceleration measurements, while challenging to implement, provide powerful tools for probing internal structure and composition of objects that cannot be studied through direct sampling. These techniques become particularly valuable for studying objects that pass through our solar system too quickly for detailed spacecraft reconnaissance missions. Unlike long-period comets that return predictably to the inner solar system, interstellar visitors offer only brief opportunities for observation before disappearing back into the galactic void. The mass anomaly of 3I/ATLAS might also provide insights into fundamental physics operating under conditions not readily accessible in terrestrial laboratories. If exotic materials or unusual physical processes explain the object's properties, studying these mechanisms could expand our understanding of matter behavior under extreme conditions. Such insights might prove relevant to fields ranging from condensed matter physics to high-energy astrophysics, where similar extreme conditions occur in environments like neutron star surfaces, black hole accretion disks, or the cores of giant planets. 3I/ATLAS serves as a natural laboratory where these exotic conditions remain stable over cosmological timescales. The philosophical implications of discovering objects with properties that challenge fundamental assumptions deserve consideration alongside the scientific questions they raise. Science progresses through the continuous process of developing theories, testing them against observations, and modifying them when discrepancies arise. 3I/ATLAS represents exactly this type of observational challenge that drives scientific advancement. The history of astronomy includes numerous examples where anomalous observations initially appeared to violate well-established principles before ultimately leading to deeper understanding. The precession of Mercury's orbit eventually revealed the need for general relativity. Unexpected galactic rotation curves led to the discovery of dark matter. The accelerating expansion of the universe necessitated dark energy. Perhaps 3I/ATLAS will join this distinguished lineage of cosmic anomalies that forced expansion of scientific understanding. The mass mystery it presents might ultimately reveal new aspects of physics or previously unrecognized astrophysical processes that operate in the extreme environments characterizing interstellar space. The interdisciplinary nature of the challenges posed by 3I/ATLAS illustrates how modern astronomy increasingly requires integration of insights from multiple scientific fields. Understanding this object may require contributions from planetary science, stellar astrophysics, condensed matter physics, chemistry, and even materials science. Such interdisciplinary collaboration often produces unexpected insights that transcend the boundaries of individual scientific disciplines. The study of 3I/ATLAS might catalyze developments in techniques or theoretical frameworks that find applications in entirely different areas of scientific research. As this ancient wanderer continues its journey toward the outer solar system and eventual return to interstellar space, it carries with it the potential to transform our understanding of cosmic processes operating on scales ranging from individual objects to entire galaxies. The mystery of why 3I/ATLAS weighs too much may ultimately reveal that the universe contains forms of matter and mechanisms of organization that remain largely hidden from current scientific understanding. The cosmos continues to surprise us with phenomena that challenge our assumptions and force expansion of scientific paradigms. 3I/ATLAS serves as a messenger from the vast spaces between stars, reminding us that the universe likely contains wonders we have yet to discover and processes we have yet to understand. In seeking to solve the mystery of its excessive mass, we embark on a journey of discovery that may reveal new aspects of the cosmic environment we inhabit and our place within the grand tapestry of galactic evolution.